Alright, in this video we introduce the notion of differential operators. That is, we regard the operation of differentiation as an application of something called differential operator to a function. So let's see an example. So if we have a function f of x and its first derivative with respect to x, that is this. Okay, we regard this as operating the partial differential operator, dx, to function f. So the input is this function, and we apply this operator to have this partial derivative. Okay, so this operation is not a function. It's not a constant, it's not a function, it's something different. So we call it operators. Okay, and similarly, we can introduce the differential operator with respect to y. So if we apply this to function f of x, then we have this partial derivative, and so on. And we can introduce more general differential operators or any different operators. So let's say a and b are some real numbers. Then we introduce a new operator called d, that is a times the differential operator with respect to x, and b times the differential operator with respect to y. So this is a new differential operator. So if we apply this d to a function, for example f of x and y, then what we have is this. So this is just the definition of the differential operator, and so we apply this from the left, okay, so this is distributed. So we have a times f of xy and b times dy f of xy. So that is a f x and b f y. So this is the effect of the application of this new differential operator d. Okay, so this operation is not commutative in the sense that if we apply this from the right, the result is different from the case where we apply it from the left. Okay, so if we apply this operator from the right, what we have is this. So that is f of xy a and f of xy b. So this is a number, so we can swap. They commute, in other words. And we have this. We have no derivatives here. What we have here is another differential operator. Okay, so this is still an operator, not applied yet. So in general, applying the operator from the left is different from applying the operator from the right. So they do not commute. We can also compose two different differential operators. So let's say we have d and e, which are operators, differential operators. Then the product between two different operators is defined by its effect on a function. So this is defined by this. So first we apply E, then we apply D to the result. So this is the definition of the product between two differential operators. For example, we have this partial differential operator, and let's say D and E are both this one. So D, E, F means, so by the definition, we have this. So first we apply inside here, so that is this. So partial derivative with respect to x, but D is also the same thing. So in this case, it becomes the second derivative with respect to x. So that means dE is a differential operator defined by this. Okay. So to be explicit, this is like this, and this is equal to this. So it's very formal, but it's very convenient, and it makes sense. And of course, we can combine these. So differential operator, partial differential operator with respect to y, and partial differential operator with respect to x. Then, of course, this is equal to this differential operator. This is x. This differential operator. So this is second order differential operator, which can be obtained by composing two first order partial differential operators. And here's another example of a differential operator. We call it delta. We write delta, and this is defined as this. Okay, this operator is called Laplacian. Actually, two-dimensional Laplacian. Of course, this is named after the mathematician Pierre-Simon Laplace. So what this means is that if we apply this operator to a function, then we have this f xy so it's the sum of second derivatives with respect to x and with respect to y. So this is the effect of the application of the Laplacian. So this is fxx and fyy. And here's another example, which is it's an upside down triangle. It's called Nabla. This is actually a vector differential operator. So in two-dimensional case, we have something like this. So this is an ordered pair of two differential operators. And the first one is the one partial differential operator with respect to x, and the second one with respect to y. Okay, we can treat this as something like a vector of operators. So if we apply this operator to a function, what we have is this. So we consider this function as a scalar. So it's just like a vector scalar multiplication. We apply this operator like this. So f and this one, y. So now this is a vector in two-dimensional space, right? So, and each component is a partial derivative with respective variable. And if we have a vector valued function, so let's say u, that is u1 and u2. So this is a vector valued function. And since this Nabla, let's write Nabla, this Nabla is a vector and this function is a vector, then we can have the scalar multiplication or dot product. Okay, so Nabla dot u is, remember the definition of dot products? So that is this times this plus this times this. So that is first component times the first component plus the second component times the second component. Okay. So we have these partial derivatives, sum of partial derivatives. Yeah. We can also take the dot product between Nabla with itself. So in this case, this becomes, of course, dx dx and dy. That is the second derivative differential operator, which is the Laplacian. Okay. The Laplacian as we define here is the same thing. So these operators become handy in vector analysis or vector calculus. Now let's consider this differential operator again, a and dx and b and dy, and a, b are real constants. Okay, so d squared is of course d times d, that is this. So if we expand this, we have, so just write it more carefully. So this is the same thing twice. So this times this, we have, well, constants are just constants, so it's commutative with differential operators. So we have a squared and second order differential operator. And this times this is this ab and xy. And ba is equal to ab, they're just real numbers, constants. So we have and y dx and plus this times this, we have squared and dy squared. Okay, now if we only consider functions that are of class C infinity, so smooth functions, then this and this are the same thing. So we can swap the order of differentiations here. So we have something like this. 2ab, so this ab, this ab, and dx, dy, plus b squared, y squared. Okay, so this is just like expanding a plus b squared, right? So this is a squared to ab plus b squared. So instead of a and b, we have a and differential operator with respect to x, and b times differential operator with respect to y, and we get a very similar thing. And in general, we can continue for any powers. Okay, so a d dx plus b d dy to the power of n. Okay, by using the binomial theorem, this is expanded as this. So k from 0 to n, and n choose k, and what is it? A to the power of k, and b to the power of n minus k, and this one, so dn dx k dy n minus k. So this is yet another differential operator, but this is nth order differential operator. And of course, this n choose k means this. N factorial over k factorial times n minus k factorial. And of course, the previous example, this example is a special case of this relationship when n is equal to 2, and you should try that. Of course, you should know that this is only valid for functions of at least Cn, of class Cn, okay? N times continuously differentiable functions. Otherwise, we cannot swap the order of differentiation with respect to x or with respect to y. So this does not hold. Okay, so you should be careful when applying this relationship. Okay, that's it for this video, and we will see some application of this idea in the next video. There we will discuss a multivariate version of the Taylor's theorem. See you later.